You guys have looked at a bunch of videos and stuff about waves in general, one-dimensional waves, two-dimensional. You guys have looked at reflection and refraction and diffraction, and we've used sound, we've used light, we've used water waves, we've used ripples and ropes, we've used lots of different stuff. But now we're going to start focusing on more specific kinds of waves. And we're going to start by focusing a little bit more on sound and how sound works and some of the stuff that we can actually do with sound. Now, first of all, if you remember what kind of wave it is, it's a very, 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 very common longitudinal wave. Not a transverse wave like water or something like that, but it's a very common longitudinal wave. And of course, with that longitudinal wave, we've got the combination of compressions and rarefactions that allows it to move along through the medium. Okay, so let's review that a little bit. I'll show you a little something here. There it is right there. So we're talking about the particles and that kind of stuff and it moving through. So here we have our little speaker, and we'll sort of send a little pulse through, and you can see as we have it go through, there we go. See, the particles are always moving, and we can send a pulse, and you can see how it's a little wave coming. And this part here, there's low density of particles. That'll be the rarefaction. And on either side, there you go, you can see there's higher concentration of particles. That'd be the compression, okay, as it moves away. And we can even have like a continuous set of pulses going. So here we just have continuous waves, and this is sort of what sound, if you could actually see the air molecules, this is sort of what sound waves would look like. So you can see a lot better now, and then we have a continuous wave. We've got our nice compressions where there's lots of particles, and we have our rarefactions as well. And we can even speed this up a little bit. And of course, real sound, of course, is way faster than this, going around 340 meters per second. But this is sort of what it would look like, something like that. Okay, our compressions, refractions, and notice that the particles don't actually go anywhere. We were talking about this, like waves are the movement of energy from one place to another, but the particles overall, their overall position doesn't change. So these guys are sort of like wiggling back and forth, but they don't actually go anywhere. Okay, so that was the basic stuff that you guys looked at in terms of waves and basic longitudinal waves at the very beginning. Okay, all right. So if we expand on that in terms of sound as well, there are two main quantities that you often look at in terms of sound. One of them that's super, super simple that you can change is the frequency. The second one is the amplitude. These are both quantities that we have looked at before. The speed of sound is usually pretty much stable in whatever environment you're in, but frequency and amplitude are the two that often get changed. And when you change the frequency, this is what people often refer to as pitch, with like high tones and low tones and that type of stuff. And we can hear about 20 to 20,000 hertz. That's about what we can hear. So you got the lower ones, you got the higher ones. So if you change the frequency, you're actually changing the pitch. That's what's actually happening. Amplitude, though, this is a different thing that often is changed with sound, and this is what actually changes the volume. So when you were adjusting the volume of sound, you were actually adjusting the amplitude. And the amplitude and volume are connected to each other. So if you go back to that little simulation thing again and go back to our little particles moving here, we got this is a medium amplitude. We're looking at frequency first. So this is a really, really high frequency. So since the frequency is high, the wavelength is going to be low, because you have the formula V equals F lambda, the wave equation. Higher frequency means lower wavelength. And if I take the frequency and I reduce the frequency, you can see the waves get a lot bigger. So before, when we had the higher frequency, we had one wave from about here to there, and now the waves have gotten a lot bigger. So as you increase or decrease the frequency, that changes the wavelength, and that changes the tone. So this would be a lower tone, because it's a low frequency, high wavelength. And if we crank it up again, this would be a higher frequency or higher pitch or tone with a lower wavelength. Okay, now we'll put that back down to medium, and let's change the amplitude. So if the amplitude is really, really low, okay, this would be like a lower volume. So it's really kind of hard to see the crests and troughs because it's so quiet. There's not much difference between the crests and troughs. If we increase the amplitude a little bit, now you can start seeing it a little bit better. Okay, you can sort of see the waves a little better. But if we crank up the amplitude a lot more, now you can easily see them. So these waves are the exact same size they were in the lower amplitudes, but the volume's higher, which means the difference in pressure between the particles, between the rarefactions and the compressions, is much greater. Okay, so this is high amplitude, same wavelength. Go back down to a lower amplitude. The waves are still the same size, but the differences in pressures have definitely changed. Okay, so those are the things that change with frequency and amplitude. They control the pitch and they control the volume. So the volume a little bit different, but it's sort of like the difference in pressure. Okay, so it sort of changes the difference in pressure, you know, a little bit of difference, a huge difference, and that changes the amplitude, which changes the volume. So you put your hand in front of a speaker and it's really quiet, you really don't feel anything. But if you crank up the volume in front of a big speaker, you can feel the amplitude difference, and that's just the bigger volume. Okay. All right. Now, a big thing about sound and producing sound is you have to use resonance. Okay, and to create sound and to make sounds, that type of stuff, you have to use resonance, and you have to create standing waves in different types of structures to actually create sound in lots of different ways. There's lots of different ways it's actually done. Let me show you something of that as well. So here's a little video of it's actually called a Rubens tube. I have one in my lab, and if we were in my lab, I would show you mine, but unfortunately we're doing this online right now. Basically what it is a long metal pipe. Mine is 4 feet long, I believe. No, I think it's maybe 5 feet long. And it's basically a pipe with a whole bunch of holes drilled into it. One end is sealed, the other end has a speaker attached to it, and then you fill the whole thing with gas, like in a chem lab. And then you have the gas go through and basically becomes a whole bunch of tiny laboratory burners stuck together. And then what you do is you put sound into it, and the flames will dance. So here, this pipe is going, and we've got sound being pumped into one end, and you can see the flames bob up and down when the compressions go past when the music is playing. Okay, now there's something else you can do with this as well. If instead you only put a single tone into the pipe, and again, we could have done this in my lab, but we're doing this online. If you only send a single tone through the pipe, you can actually create a standing wave. And you can see the sort of like the crest. So right here, these higher points, those are the crests, so there's higher pressure, and then there's the rarefactions where there's lower pressure. So you could actually measure the distance between the flame tops, and that's the actual wavelength inside. And when you can get waves to fit perfectly in a structure, this is resonance. This is create resonance. So it works really, really well because you can actually see the actual waves inside the pipe, and it shifts a little bit, but you can actually see the actual structure of where the compressions must be and where the rarefactions must be in order to make this thing work. And this is the idea behind putting standing waves inside of structures to actually create resonance. Okay, so we can use resonance, and we do that to create standing waves inside of structures in order to create sound. Now, there's another part to this as well, because when you are able to do this, it will sort of naturally vibrate when the waves actually fit inside, and when this happens, this amplifies the sound. I'm going to show you something else that shows this really nicely. So here we have a video with a guy. He's a professor from the States. He's got this really cool little apparatus that I also have, but again, not my lab, so we'll show it to you this way. Basically, it's a little swinging piece of wood with 8 different spheres attached to it, but they all pair up. And what he does is he takes it and he's going to pull back one of the spheres, which is going to cause the entire thing to shake. So he pulls back that yellow sphere, and when he pulls back the yellow sphere and gets it to swing, it will create vibrations. You can see the whole thing moving already. So there's vibrations going through the entire system. All the strings, all the spheres, everything is getting vibrations from this yellow one over here. But it does a specific size of vibrations because of how big it actually is. And you can see all the other spheres are wiggling, but the other yellow one is going way more than the rest. And that's because it matches in size. So the vibrations created by the first one fit so perfectly within the other yellow one because they match up in size. The other yellow one is starting to resonate, and it sort of amplifies naturally the vibrations that are going into it and ends up swinging way better than all the rest. Okay, so that's the basic idea behind resonance. You create waves, you create standing waves inside of objects. If they fit nicely, they will naturally vibrate with the object and they'll amplify the sound. And that's how resonance works. And this is the general idea behind how all musical instruments work. This is how all sound production works of any kind. Your vocal cords, a violin, a guitar, a piano, a trumpet. It makes no difference. They all do the same type of thing. They naturally amplify sounds in order to make it work. Now, you may even notice sometimes, you're listening to music really, really loud or something like that, and all of a sudden a picture starts vibrating, or something that's sitting on your shelf or something just starts vibrating and rattling really, really loud. Well, it's resonating. For some reason, certain frequencies, certain waves are fitting within that structure. It's beginning to vibrate, and it amplifies it. Same thing, you're driving a car, especially in winter when the parts of the car start to get smaller where the trim, so they loosen up a little bit. You're driving, all of a sudden a certain part of the car, like a door panel or something, just starts rattling for no reason. Well, because there's vibrations going through it, they just happen to fit perfectly, and it causes it to resonate. And there's lots of different things that actually cause resonance, that type of stuff. Okay. A great example is if you play baseball or something like that, and you hit the baseball with the bat, and you hit it the wrong spot, like you hit it at the very tip of the bat or really close to the hands, it will hurt your hands. We often call it cracking the bat. And the reason why it hurts so bad is because you're hitting it at a place which will cause the bat to resonate and vibrate. And it takes all that energy away, and the ball doesn't go nearly as far. But if you hit that ball in the sweet spot, which is sort of like the middle-ish of those 2 points, the reason why that's the sweet spot is because when you hit it there, it creates waves in the bat, but it's not causing the bat to resonate, and you're not losing all that energy, and it works better. Same thing applies to tennis and golf and hockey or anything you want where you're making contact with something. Where you hit it makes a big difference on how it'll actually go, and often it has to do with creating waves inside the structure. Okay, so resonance is actually part of a whole bunch of different types of things. So let me show you something else involved with resonance. So here's a little video of a street performer, and I'm not sure how well the sound is going to come through with this because I'm playing it on my device like this, but we'll see how it goes. And they're playing the glasses, and it's all about resonance. So the glasses are different shapes, they're different sizes, they have different amounts of water in them. When you change the structure, you change the resonant frequency. So as you change the frequencies, you can play music. So we'll get this guy going here a little bit. Okay, so absolutely amazing. So, and that's all resonance. And there's no difference between that and all other musical instruments where you change the length of a string, the length of an air tube, the length of anything, the size, which changes the resonant frequencies that will work inside of it. So this is just a wonderful, wonderful example and amazing talent to do something like this, but it's all using the applications of resonance.